No, can you hear me? You're muted. Can you hear me?
Yeah. Good morning, Girish.
Hey, good morning, Alpha. Katie, how are you?
Yeah, fine.
No,
Yeah. ಇಲ್ಲ ಕಾಲೇಜಲ್ಲಿದ್ದೀವಿ.
ಇದು ಆಫೀಸ್ ಅಥವಾ ಕಾನ್ಫರೆನ್ಸ್ ರೂಮ್?
ಇದು ಸಿಲ್ವರ್ ಜುಬ್ಲಿ ಕಾನ್ಫರೆನ್ಸ್, ಇದು ಸೆಮಿನಾರ್ ಹಾಲ್ ಕಾಲೇಜ್.
Good morning, Ganjal sir.
Good morning, Anil Kumar.
Anil Kumar Dandekar sir.
ಹೇಗಿದೆ ಆರಾಮ?
ನಾ ಆರಾಮಿದ್ದೀನಿ ಸರ್, ನೀವು?
ಆರಾಮ್.
ಬಹಳ ದಿವಸ ಮೇಲೆ ನೋಡ್ತಾ ಇದ್ದೀನಿ ಸರ್ ನಿಮ್ಗೆ. ನಾ ಈಗ ಸದ್ಯಕ್ಕೆ ಮಂಡ್ಯದಲ್ಲಿ ಇದ್ದೀನಿ ಸರ್, BCF ಮಂಡ್ಯದಲ್ಲಿ ಅಸೋಸಿಯೇಟ್ ಅಂತ ಹೇಳಿ ಜಾಯ್ನ್ ಆದೆ. ಮೊದಲು ರಾಯಚೂರಲ್ಲಿ ಇದ್ದೆ. ಗೊತ್ತಾಯ್ತಲ್ಲ ಸರ್ ನಾ ಯಾರು ಅಂತ ಹೇಳಿ? ಗೊತ್ತಾಯ್ತಲ್ಲ ನಾ ಯಾರು ಅಂತ ಹೇಳಿ ಸರ್? ನಾನು CT ಕ್ಲಾಸ್ಮೇಟ್ ಸರ್, CT ಕ್ಲಾಸ್ ಅನ್ನ.
ಎಲ್ಲ ಮನೆಗೆಲ್ಲ
ಸರ್ ಎಲ್ಲ ಆರಾಮಿದ್ದೀನಿ ಸರ್.
Hi Girish.
Devanand, how are you?
Hi Girish. Hi, good morning. How are you?
Good. How are you doing?
You look pretty same. I'm doing pretty good. You look same. You haven't
Yeah.
changed. You look as young as you were in college.
Yeah. Oh, thanks. All the
Yeah.
credit to my wife.
Oh, really? Okay. Not the extrusion. Not the extrusion products.
Yeah.
Right. So, how is the weather in Pullman?
Right now, it's as good as it can be. Good summer weather.
Okay.
Very nice weather right now. Yeah, for another month or so, it'll be nice, and then it'll slowly start getting cooling down.
Yeah.
How's Raichur weather? Hot?
It is just like Simla.
Raichur weather this time it's pretty good, and we are receiving a lot of rain this time.
Oh, nice. Very nice.
Yeah.
It is almost
Mathal.
Simla.
ಹೇಗಿದೆಯಾ ಮಠದ್? ಆರಾಮ?
How are you, sir?
Very good.
Nice to
Yeah.
see you, sir, after a long time.
Yeah, long time. Yeah.
When you are visiting to Raichur?
Raichur, maybe another couple of years. Once we find a vaccine, maybe.
Yes, sir. Once again, we will go to Mantralayam.
Yeah.
Bring some vaccine, Girish. ಸರ್ ವ್ಯಾಕ್ಸಿನ್ ನೀವೇ ತಗೊಂಡ್ಬರ್ಬೇಕು ಅಲ್ಲಿಂದ ಈಗ. ನೀವು ವ್ಯಾಕ್ಸಿನ್ ತೊಗೊಂಬರ್ರಿ, ನಾವು ಹೈಡ್ರೋಕ್ಲೋರೋಕ್ವಿನ್ ಕೊಡ್ತೀವಿ.
ಹೈಡ್ರೋಕ್ಲೋರೋಕ್ವಿನ್ ಎಲ್ಲ ಕೊಟ್ಟಾಗಿದೆ.
ಉಳಿದಿದ್ದು ಕೊಡೋಣ, ಏನ್ ಚಿಂತಿಲ್ಲ.
How is your family and all, sir?
Very good. They both are fine.
Girish, Desai sir is there. Desai sir.
Oh. Hello, sir. How are you?
Sir, unmute ಮಾಡ್ಕೊಳ್ಳಿ.
ಮಾಡಿದೆ. How are you, Girish?
Very good. ನೀವು ಹೇಗಿದ್ದೀರಾ?
Fine.
Very good. Good to see you.
Yeah. 3 years back we met, I think.
Yes, sir.
Yeah.
Dharwad.
Arvadnalli.
Into Dharwad, no?
Yes, sir.
During that time, I think. After that,
Yeah,
hello?
was that 3 years ago? That was in your office, right?
Yeah, I'm in the office.
Yeah.
After that, you have not come, I think.
One time I did last year. It was a quick trip, but then no, didn't stay for too long.
How is situation there?
Well, the university town is fine. In Pullman, there's not much.
But outside, it is tough.
If you go to Seattle, bigger cities, then ಅದಕ್ಕೆ March Linda, I haven't traveled since March. I've been in home or to the office and home. We go to office. Labs are open.
Yeah. Here also same situation, almost.
Classes, everything is online, or you're doing?
Classes is online, but now that semester is also completed. We were unable to conduct the exam.
Oh, okay.
Again, second semester by this time it would have started, but because of this, everything is standstill. How about there?
Yeah, well, we are in the summer session right now. Everything was on. All is going to be online. 90%. Yeah, some universities are doing a hybrid, or they call it model. That means you teach face to face, but at the time you have to provide the online. So both simultaneously.
But here also they are thinking, but online I don't feel it is so much effective.
It's not.
Second thing is connectivity problem. Because in remote places, no, students complain that they don't get the net. That is the problem. Main connectivity is major problem here.
Yeah.
So we
Plus the other risk is the exams. How do you proctor? That's a
we could at least meet old students to this Henry Devanand.
ನಮಸ್ಕಾರ.
ನಮಸ್ಕಾರ ರೀಪ.
ನಮಸ್ಕಾರ.
ಹಲೋ, ನಮಸ್ಕಾರ ರೀಪ.
ಸರ್ ಆರಾಮಿದ್ದೀರಾ ಸರ್?
ಆರಾಮ್ ರೀ. We are seeing our old students, ಅಲ್ಲ?
Yes, sir.
ಎಸ್. ಮಳೆ ಎಲ್ಲ ಹೆಂಗಿದೆ ಸರ್ ಈ ಸಲ ಧಾರವಾಡ?
Since from 48 hours continuously it is raining here. Now also it is raining heavily outside. Sharan,
ಅದೇ
2-3 times I got disconnected, no?
Yes, sir.
That is because of this connectivity. ಬಹಳ ಮಳಿ ಬರ್ಲಿಕ್ಕತ್ತದ್ರಿ. Last year you could remember? Same situation. In 1 or 2 days it will be like that.
ಇಲ್ಲಿ ರಾಯಚೂರಲ್ಲಿ ಇಷ್ಟು ನೋಡಿರ್ಲಿಲ್ಲ ಸರ್ ನಾನು.
Girish, police code sir is there. Sir, namaste sir.
Police code.
Namaste. Sir. Sir, everybody is there, sir. Video on ಮಾಡಿ sir.
Oh, I see Dr. Nidoni.
Yeah, no, police code sir just now. Yeah, he has raised his hand.
ಪೊಲೀಸ್ ಗೌಡ್ರು ಬಂದ್ರ?
ಇಲ್ಲ ಸರ್, ಅಲ್ಲೇ ಇದ್ದಾರೆ ಸರ್, ಬಟ್ ಜಾಯ್ನ್ ಆಗಿದ್ದಾರೆ ಸರ್.
ಜಾಯ್ನ್ ಆಗ್ಯಾರ, ವೆರಿ ಗುಡ್.
Video it is not.
Yeah, long time. Good. How are you doing?
Very good. Yes, I'm also doing well. Fine. Thank you.
Awesome.
Good. No, once again after a long time.
Yeah.
Yeah, very good. Nice to see you all. Okay, good. Thank you. First, thanks for accepting our giving consent
Sure.
to participate in this training program.
ನಿಡೋಣಿ ಸರ್, ನಿಮ್ದು ವಾಯ್ಸ್ ಕೇಳಿಸಲ್ಲ, ಜೋರಾಗಿ ಮಾತಾಡ್ರಿ, ಇಲ್ಲ ಅಂತ ಸ್ವಲ್ಪ ಸೌಂಡ್ ಜಾಸ್ತಿ ಮಾಡ್ರಿ ಸರ್.
ಹೌದಾ?
ಎಷ್ಟು ಕೇಳಿಸೋದಿಲ್ಲ ನಿಮ್ಮ ವಾಯ್ಸ್.
Now, am I audible? ಇಲ್ಲ.
ಆಡಿಬಲ್ ಇದೆ, ಬಟ್ ಸರಿಯಾಗಿ ಕೇಳಿಸಲ್ದು ಸೌಂಡ್.
That is the mistake of the computer.
ನಾಟ್ ಮಿಸ್ಟೇಕ್ ಆಫ್ ಕಂಪ್ಯೂಟರ್, ಯುವರ್ ಫೋನ್. ನೀವು ಇನ್ಕ್ರೀಸ್ ದ ಫೋನ್ ವಾಲ್ಯೂಮ್ ಜಾಸ್ತಿ ಮಾಡ್ರಿ, ಇಲ್ಲಾಂದ್ರೆ ಕಂಪ್ಯೂಟರ್ ವಾಲ್ಯೂಮ್ ಜಾಸ್ತಿ ಮಾಡ್ರಿ.
ಎಲ್ಲ 100, now it is 100%
Okay.
showing volume. Okay, whatever it is.
Okay.
Fine. Let us see. I think we are all eagerly waiting for Girish presentation. Wonderful. Girish, how is COVID there?
ನಿಡೋಣಿ ಜೋರ್ ಮಾತಾಡ್ರಿ.
Hello.
ನಿಡೋಣಿ ಜೋರ್ ಮಾತಾಡ್ರಿ. We are not hearing anything.
Sir, am I audible now? Hello. No.
ಇಲ್ಲ, ಜೋರಾಗಿ. Something wrong with
Sir, you
Volume
are audible, but it is not properly. ಅಂದ್ರೆ ನಿಮ್ ವಾಯ್ಸು ಪೂರಾ ನಾವು ಗುಸುಗುಸು ಮಾತಾಡ್ತೀವಲ್ಲ ಹಂಗೆ ಕೇಳಿಸ್ತದ.
But I did hear him though. But thanks for having me. I did. So thanks for having me here. And anytime I can come online anytime and talk to any of you.
Very good.
Okay, so it is 9:58. We'll wait another 2 minutes. Is it okay, Giri?
Yeah, I'm good.
ಶರಣು
Sir, namaste sir.
ನಮಸ್ತೆ. ಗಿರೀಶ್ ಸ್ವಲ್ಪ ಮಾತಾಡಿಸ್ರಿ, ನಂದು ವಾಯ್ಸ್ ಕೇಳಿಸ್ತದ.
Girish, sir is online. Police code sir, please.
Sir, ಹೇಗಿದ್ದೀರಾ?
ಚೆನ್ನಾಗಿದ್ದೀನಿ.
Okay, cool.
I'm here at Bangalore taking treatment for COVID.
Oh, okay. Well, take good care. It's not. I hear it's not a good thing.
You say it is wow. It is wow actually. So it's since long. Okay. So I hope you are doing fine.
Fine, thank you.
Girish,
Okay. Sir. Yeah.
Girish, how are you?
Very good. Yeah.
Fine.
Good to see you.
Yeah, glad to see you.
Yeah. Anand was telling me that I still look the same from years ago. You look the same since like so many years ago.
It's many years.
Yeah.
So, are there any plans to visit?
Yeah, maybe next year, once the pandemic is subsided a little bit.
Please make it.
Absolutely. If I make it, I'll definitely make it to Raichur.
Definitely, please. Okay.
Sir, good morning, everybody. So now it is almost 10 o'clock. We are going to start the session. So Giri, you make it unmute yourself. Girish, please unmute yourself. Yeah.
Yeah.
It's fine.
You can hear me well, right?
Yeah, it's fine. Yeah. So because I took all unmuted except yours. Okay. All right. Good morning, respected our Honorable Vice Chancellor, Director of Education, all the officers of the University of Agricultural Sciences, Raichur. And this is the second day of our technical program on advanced agricultural engineering technologies for sustainable agriculture, a webinar hosted by College of Agricultural Engineering, UAS Raichur. I heartily welcome to all the officers, all the delegates, all the teachers, and all the scientists of the different parts of the country for this a wonderful webinar. So we have a wonderful personality, Dr. Girish M. Ganjal. He is an interim director and associate professor, School of Food Science, Washington State University, Pullman, USA. So he is going to deliver on extrusion processing, a look at the transformation of the major components of ingredients. So in this regard, once again, I heartily welcome to the Dr. Girish for this webinar. So may I request Dr. Ramappa Keti to introduce his brief biodata. Dr. Ramappa Keti, please.
Okay, sir, definitely. So am I audible to everyone? Okay, good morning all, respected Dean and organizer of this webinar, College of Agricultural Engineering Raichur, and key officers of IUS Raichur, and respected senior faculty members of Division of Agriculture Engineering, and fellow attendees from various part of the locations. So it is an immense pleasure, and it is a great pleasure to introduce one of the most eminent and internationally acclaimed academician, researcher, and extensional professional in the field of agriculture processing and food engineering, Dr. Girish M. Ganjal. So he is basically from Hubli, sorry, that is Hubballi, and he completed his schooling in Hubli itself, and then he completed his BTech in agriculture engineering from our institute. It is again a proud to say that he is our alumni, and he is 8th batch student and completed his BTech from College of Agricultural Engineering in the year 98. And then again, one more very important thing about him is actually he got fellowship to do his PG from one of the top institute in Asia, so that is Asia, AIT, Asian Institute of Technology, Bangkok, Thailand, and he completed his PG in the year 2000. And then he completed his PhD from University of Nebraska, Lincoln, in the year 2004, and he also completed his MBA in technology management in the year 2006. So after his his studies, and he joined MGP Ingredients MNC, so from so it is topmost MNC in US. He worked from 2004 to 2009 in MGP Ingredients, where his contribution in terms of extrusion processing and protein ingredients are worth mentioning. And again, so he worked as principal engineer, principal engineer, and again one more MNC, that is PepsiCo. PepsiCo, where he could able to work in do significant contribution in the area of extrusion and frying processes. And then so he also worked as assistant professor in By State School of Food Science, Washington State University, Pulwan from 2013 to 2018. And presently he is working as interim director and associate professor in School of Food Science, Washington State University, Pullman now. So coming to so he is having many awards and recognitions in his cap. So few to mention here is a Faculty Excellence in Extension Award for his recognition work in the innovation scope and impact extension programs and leadership. And so team interdisciplinary award in the year 2015 in recognition of teamwork on Pinon projects, and AICC International Young Scientists Research Award in the year 2012 for his contribution, strong contribution in serial science and processing. And again, he got Chairman Recognition Award in the year 2012 from PepsiCo for his significant contribution in extrusion processing and frying process. And again, he got one more very good award, that is Pursue Great Science Award in the year in 2 years, consecutive 2 years, 2010 and 2011 from PepsiCo. And he also got a Scientist Award for the year 2006 from MGP Ingredients. And again, he got one more very good. So these are graduate students of the year during the year 2040. So these are a few to mention in many coveted awards. And he got 5 patents in his name. So again, I don't want to go in detail because definitely you can see all these patents. Again, these all 5 are very good contribution in the area of research. And in terms of extension activities, he could able to mobilize around 1.2 million US dollar in terms of his academic research and extension activities. And he got grants to tune of around 7 million US dollar for research work from many international funding agencies like USDA, NSF, and WSDA, so and so. I got one textbook in his name, so that is Extrusion Cooking. So last year itself he released this book and in collaboration with elsewhere. And he published more than 60 international recognized journals, papers in the international acclaimed journals, and 11 peer-reviewed extension publications. And he attended more than 20 conference presentations and posters at international level. And with respect to his professional service, he is an associate editor for the journal Serial Chemistry Journal. And he is also a peer reviewer for 6 internationally acclaimed journals, that is Journal of Food Engineering, Journal of Cereal Science, Journal of Food Science, Food Research International, Journal of Texture Studies, Journal of Agriculture and Food Chemistry. And he is a member in more than 6 professional organizations that I don't want to go in detail. And he has guided more than 14 students, 10 masters students and 4 PhD students, and currently is also guiding 8 students. And he guided 2 post-doctor students, and 2 is going on. And again, he guided around 28 undergraduate students in research to complete for completion of their research. And this is what is a brief biodata. And again, one more very important thing to mention is he is my classmate, UG classmate. And I am proud to be a part of this wonderful team of 21 students, BTech batch from 1994 to 98. And so he is a very focused worker. He is a very highly focused and highly committed and highly is a very good passion with respect to agriculture engineering discipline. So this is what in brief is the biodata of Dr. Girish M. Ganja. And thank you very much for Girish for accepting our invitation and make it here. Thank you, one and all.
Well, thank you for brief and elaborated biodata of Girish. There is no end of briefing the activities, performance, even though he is a gold medalist of College of Agriculture Engineering, Raichur. So once again, hi RT, welcome to the Girish Ganja. Now it is time to presentation. Girish, please.
Thank you. Well, I thought you were going to just say the best part about my experience is my time in Raichur, 1994 to 1998. That was my best part.
Yes.
So You could have just said that I was from there and I graduated from there. So it is a pleasure to talk to all of you. And I see there's quite a few people on the screen who are logged in. So good morning to all of you. Okay, for me, it's evening. I just finished my dinner and I'm brushed and I'm ready to sleep. But I'm happy that I'm able to come online and present. So what I'm gonna do is, when Sharon Gada asked me to come and present, and he asked me for a topic, I said, well, I have worked in extrusion for a long time, and why don't I present on that? But instead of doing a broad introduction or talking about a specific area within extrusion, I thought, let me just give you an overview of what we know so far in terms of using extruder to create food products that are nutritious and also have a good texture. So what I would like to do is to go a little deeper into it to really tell what do each component within a food product, like starch, protein, and fiber, which are the main components, how do they change inside an extruder? And if you understand that, how you can utilize that to create products that people crave for. So that's kind of what my goal is. And I would like to bring it to a conclusion where I identify some gaps. So in the future, if people, anybody listening here, or the next generations, they can take on and continue working it. Okay, so that's my goal. So at any point you can stop me, but I think what I was told was I will go ahead and present for about 40 minutes. Then I will stop and we'll open up for questions. Okay. All right, I'm gonna share my screen.
Yeah.
All right, screen 2. You should see nothing, right?
Yeah.
Okay. Okay, put it in the presentation mode.
Yes, fine.
Okay, excellent. All right, so that's the title of the presentation. So if you see that, then what I will focus on is to how do the ingredients change inside the extruder as they're passing through. That's my goal. Okay. So this is the outline. We will talk about where extrusion is used. That might be very common knowledge, but I'll try to show you some examples. Then I'll try to break down the extruder so that you can see what is in an extruder and how things are processed in it. And we'll focus on two phenomena that are used commonly. One is expansion and one is texturization. So expansion is what is used to make products like kurkure in the market in India. And texturization is in the latest, you must have seen a lot about plant-based meats in the current times, and that's what the process is used to make the ingredient that goes into making the plant-based meats. And then I'll close out with going into how starch changes, how protein changes, and how fiber changes in an extruder. Then I'll close with my final thoughts on it. Okay. All right, so applications-wise, extrusion is a technology that is used very widely. I mean, I can guarantee if you have eaten any product that is processed, then you would have had something that was extruded. In India, the common one is kurkure. If you had kurkure or any other version of kurkure or different brands, those are made with extruder. So animal feed, pet food, fish feed, majority of them are made with extruder. And in terms of human food, breakfast cereals, snacks, dough, textured proteins, jellies, candies, like if you know M&M, a lot of those products, and gums, like chewing gums, those are made with extruder as well. And sometimes these are also used for modification of ingredients that are further used in making different products. And then in terms of non-food, pretty much any packaging material, like any film, packaging film, packaging boards, tubings, pipes, all those are made with extruder as well. If you really go back at the history, extruders were found applications in non-food first, and then that was transferred over to the food industry. Here are some examples of the products that are made with extruders. And here's a few more. You can make different shapes, different textures. You know, some of the pictures you see on the screen, like for example, this one on the far right that I'm showing my cursor, that's used, that is made using a co-extrusion technology, which you bring in a different ingredient in the die, and one ingredient is extruded through the main extruder. So sometimes you can do that. You can pump an ingredient in the die to create this co-extruded product, or you can use two extruders to make a single product. You know, you can really, it's the innovation is endless when it comes to extrusion. And this one, what you see on the picture there, that's a third generation product. Or in India, when I was growing up, there was a product called fryams. You know, you take home and then you fry it. So that the base product is made using extruder, but it's heavy, dense product that you go back, take it home and finish frying. And you can see some of the colored products, different shapes, different colors. And this one here is a textured protein. It's like a strip, a small chicken strip made with plant proteins. And these are examples of fish feed and pet food. And this one is a textured protein to mimic a chicken product. And this is basically to mimic a beef product. And this is showing some textured products. So what a texture is, you take about 60, 70% protein ingredient and extrude it so that you can create the fibers that you see here on the right picture. And these fibers is basically a plant-based. Then they take this and put it into making a meat analog or a fake meat that is more commonly, is flourishing. That industry is growing a lot here, at least in the US. Okay. So now I'm going to go into providing a very brief overview of the extrusion process. And the best way I thought to do this was using a picture. See the schematic that we drew, one of my students drew this in a recent book that was published. So typical extruder consists of a motor. It's required because that's what supplies the energy. And you have a one screw or two screws. By looking at this picture, this is a twin screw. And that's because the screw is parallel throughout. And you can see a lot of different types of elements on it. If you here at the bottom are the real pictures of the elements that you can modulate your profile so you can put different levels of energy into the material. So as the product is fed here, where my cursor is, where the feeding port is, this product is raw product like raw starch as a granules. And goes in as a flour, but there's a lot of porosity in it, even though in the picture it looks too much porosity, but in reality it's a flour, but it still has porous nature in it. So there's a lot of air in it. That material goes into the extruder. It gets compacted as it goes towards the end. On this side, on the far right, is the die. So as it gets compacted, the compaction along with the shear from the screw, which actually creates shear between the particle to particle, and that transforms the material. It goes through a phase transition and melts. That's what we use the term melt. And you can see the picture here showing on the left side, it's blue, and as it goes toward the right, it's red. That's basically saying that it gets hot. So, and once it's melted, it goes through the die plate easily and comes out. And if it's a starchy material, in the range of moisture, about 15 to 20%, it tends to puff. And it creates that puffy material that becomes a snack base, like a kurkure base. And the die, an example of the die is in this picture here, which shows the small holes into it, about 3 to 4 millimeter diameter holes. And so that's a very typical extrusion process for making high puff materials, high puff snacks or cereals. And in general, it's really important to understand what happens inside the machine here. If you go inside the machine, what kind of conditions do you see? So in the last zone here, last zone and the die, that's really what we're focusing on. The temperature there will be anywhere from 120 to 160 degrees centigrade. And the pressure is pretty high as well, so 200 to 2000 psi. And moisture content, depending on the type of the product, can be from 15 to 35. So if you want to puff the material, you use lower moisture. If you want to not puff the material, typically it's a higher moisture. And another important factor is the time that the ingredient spends inside the machine is less than 45 seconds. So it's a super short time, very high pressure, and high temperature. So imagine under these conditions, when the temperature is more than 100, that means you're boiling the water. The water should boil, but it is under high pressure inside a closed system. So that effectiveness of the temperature is even more higher. And that's why when it releases to the atmospheric pressure, that pressure differential is the reason why the moisture, which is in a liquid form, converts into vapor and creates the puffing action. And here is an example, a picture of a twin screw system. This is a laboratory scale machine, which is in our laboratory here. So when I came to WSU about 8 years ago, that's when, the way it works in the United States is, when you're hired as a faculty, you're given a startup money, you go start. It's like starting a business, basically. So I had invested into buying a machine. So this is a machine that we ended up getting. We still use it. So that's the machine you see here, 4D lower D long machine with modulated profile and a clamshell system. And it has a feeder in the back there, and the product is running. Some product is coming out here. On the right side is the screw profile. And this here is a machine, a picture I took back at some company. It's a single screw system. I just wanted to show you how they look like. So single screw system are typically short barrel, which are used for making puff snacks. So if you're making a corn puff, this is the machine they use. And you can see here, there's a die, and where I'm pointing to, those are the die holes. And in the back here is the barrel. And that's a sketch of that is done here. So it's a short barrel, and at the end you have the die. There's really not a lot of heating going on here except the shear. Okay. And this is a twin screw Klextrol system manufactured, and it's a French machine. They were one of the early ones who started making the machine, along with them, the Wenger and the Bueller. But now there's like hundreds of manufacturers across the world, including India, Korea, and China. This is a Wenger system. I always show this because it gives you a realistic picture of how a production system goes on. So you have a hopper here, which feeds the material into a preconditioner. Sometimes you have it, sometimes you don't. So preconditioner is used to condition the material ahead of time so that you can cook a lot more in the barrel. Comes out, then you have a suction system or aspirator that takes the material and conveys it to the dryer. It's always good to have a suction system here because the moisture coming out of the machine can condense into this die cutter and end up clogging the area quite a bit. So here are some examples of Bueller systems. There's a lot of flexibility in extruders. So for example, this one is a really long barrel. Some I have seen all the way to 40, even on large machines, the diameter of 140 millimeter. And like this one says, this is they have up to 175 millimeter diameter. That's a big machine. Machines that produce anywhere from 4,000 to 8,000 pounds an hour. So about 2,000 to 4,000 kilos per hour. And this is a 144 millimeter machine. I worked on this machine in my first job after coming out of college in Kansas. And this was a real good experience working on a huge machine. We used to make about 2,000 kg per hour from this machine. All right, now I'm going to jump into expansion process. I briefly told you how it goes. Just a closer look at it. Product coming out of the machine, puffs right away, immediately. That's what we call a direct expanded product. And you cut it on the face of the die using a cutter or a blade, and that gives you the product. And if you run the blade faster, you get a smaller cereal. If you run it slower, you get a snack product. And the main thing about this product is when you cut it open, you will see the cell structures, and the right side are the SCMs, and the left side are the taken using the light microscopy or even a regular camera. So you see there's an open cell structure, and that's what you see here. So puff products are characteristic like this. They always have this puffed cell structures. And that's what dictates how it tastes in your mouth, whether it's puffy or it's crunchy or crispy. That is all directed by the texture of these cell structures. Most often, starch is used. Starch is a major ingredient, and nowadays people are trying to use proteins, but majority is still a starch. And other ingredients they commonly use are nucleating agents or expansion aids, as we call them. We can manipulate the cell structure by using different ingredients in it. I'm going to go through the texturization process. So this is there's two categories in texturization. One is the TVP, which is the textured vegetable protein, and another one is the high moisture meat analog. And essentially the process is the same, except for the TVP is run under lower moisture, so anywhere from 30 to 40% moisture. And high moisture meat analog is run with about more than 55% moisture content. So this one has a lot of moisture coming out of the system, and you create this fibrous structure by using a cooling die or a long die. So you build a structure using the cooling die and a long length of it. And I'll show you a little later how it works. And in TVP, the dies are very short, and you're mainly looking for this long fibers in this one. And the main difference between these two, the high moisture has really, really small cells, air cells in it, while the TVP has big pockets of air in it, almost like expanded powder. Okay. I'm going to jump into transforming the raw materials. So this is where, when we learn about ag engineering or food engineering, it's always important to learn the chemistry. I learned that over time. Back when I was doing my undergrad, I learned some, and later in my grad school, I spent a lot of time learning chemistry. Because chemistry, when you combine with engineering, you can do wonders with it, right? That's essentially what you learn over time. So that's how, what I've come to focus in my research or in our group research is, it's not just the engineering, but it is also a combination of food chemistry and food engineering together. All right, so you could take any food product on the market, whether you eat rice or sambar or whatever else, or idli, anything you eat, you can take that and break it into these major components. You have the carbohydrates, you have the proteins and the fats or the lipids, and minor ingredients, which will be your different elements and sodium and other things that you have in it. But bulk of it always is a carbohydrate, unless you're specifically trying to get a high protein product. And the carbohydrates consist mainly starch, but other things like gums, sugars, they're also called carbohydrates. But we're going to focus only on starch as a carbohydrate. So what happens to the starch when you run through an extruder? Right? So let's walk through that. You put in the raw material, raw starch, which is in the form of granules. Those are what I call a little egg-shaped particles. And the granules have, amylose, amylopectin, and all that, but let's just say those are little balls, spheres. And then you run them through the extruder. They get gelatinized because of the moisture content going in it, but in an extruder, the moisture content is really low. So you don't get a complete gelatinization that they call a traditional gelatinization, which happens in excess moisture. So here, it's always a combination of that and mechanical damage or mechanical breakdown. That's what happens to it. And then you get these free polymers, and the free polymers get aligned inside the die finally before it exits the die. And as it exits the die, then the water is converted into vapor as it comes out. And then you get this puff material. Okay. The pressure drops to the point that is the maximum expansion you get. And then if your temperature does not equilibrate with the atmosphere for a long period of time, then the material starts shrinking, so you get some shrinkage. So every product out there has some sort of a shrinkage. You cannot avoid it. You can minimize it. So that's what we call inside it's a melt and it comes out, then it's for some time it's viscoelastic. And once it's completely equilibrates with temperature and pressure, then it solidifies. And this is how it looks like inside the extruder. So you had to go from the flour, like, when you make chapati or roti, you get the flour, that's the flour you put in. Inside the extruder, it has to go through this glassy phase, then only it'll puff. And what happens if you follow the phase diagram, you're essentially taking the material and going it through the glass transition point and then passing it on to the melting point, and then you reach this melt or gel phase that I showed you in the previous picture. And when you come out of the extruder, the temperature drops suddenly, that creates the moisture flash off, and you bring the product back to its glassy state. That's the phase change we do, and that's what we call a cooking process. All right. So that's what happens to the starch, and let's see what happens to the fiber. So fiber is one of the most inert materials you can get, right? Fiber is essentially made up of glucose compounds or units, but then when you consume it, it's not going to break down easily, right? In your large intestine, it's going to go there in the large intestine and stay there and help you build the good bacteria, right? And that's the purpose of the fiber. So when you put it in an extruder, I mean, if you logically think about it, it's going to do the same. It's not going to try to break down easily. It's not going to go through the phase change like what the starch does. So fiber remains as it is under the conditions that we typically process. The only thing that can happen to the fiber is it can break up into small pieces. So when you put the fiber into the starch matrix and send it in, so if you remember, we saw this cell structure before. With no fiber, you really got a nice puff. But once you add some fiber to it, where does it go? It has to go and sit in that film, in that wall, in that film that is created from the starch. Essentially, the fiber has to go and sit there. It acts as an inert material that has to be held in the starch. So if you add, in this picture, you see like you added a 6% fiber that starts breaking up the structure. So you get this accumulation of fiber throughout the matrix very randomly without any uniformity. But if you add it at a lower level, let's say 2%, it blends in pretty well, you don't see it, and it's not going to break the structure. But if you add a lot of it, then it's going to break up the structure quite a bit. And there's quite a bit of research done on how to incorporate fiber into the puff products. We can go in depth about it, but essentially, to date, what we know is if you break the particles into really small size, then we can incorporate up to 20%. Or you can go the soluble fiber route, you can incorporate maybe up to 30% of fiber into product. And if you don't, if you use a typical insoluble fiber at a higher level, people won't like it. You won't eat the product in the market because it'll taste like cardboard. And here's a sketch showing what happens without any fiber. This is what you see. That's the air pocket, that's the cell wall. And as you put the fiber, it has to go and sit in that cell wall. But if you put too much, it's going to break the structure and it will collapse, it will shrink. But you can take that fiber into small particles and you can put a little more. But if you have bigger particles, it's going to break up the structure. So that's kind of what we hypothesized. This is one of my students did the work. That's the best way you can do it. So usually if your particle size is below 125 microns, then you can incorporate it. All right, so to summarize, this is what happens to the starch inside the machine. And that's what helps you to create that structure. And this is what happens to the fiber. It remains as it is, but except it might break down into smaller particles if you put a lot of shear into it. All right, now let's go into the protein. Proteins have a tendency to denature when you put shear or heat or change the pH. We're not going to change the pH in an extruder. Typically, you use shear and heat. And what it does is it basically loses its original functionality. So it will lose its quaternary structure, and its tertiary structure perhaps, and it'll realign inside the machine. So when you try to make a highly expanded product, so let's say you want to make a kurkure with a high amount of protein in it, it's not easy to do it unless you use a highly soluble protein. That means if you break down the molecular weights of the protein to smaller structures, smaller peptides, or then you can incorporate higher amount of that into the finished product. But if you use, let's say, wheat protein or soy protein or pea protein, as it is with high molecular weights, you can only incorporate a little bit. If you put too much of it, even more than 10%, it's going to tend to change the structure and make it pretty hard. All right. So coming back to this, the other thing you can do with the proteins is, I mean, they tend to texturize. When I say texturize, that means they create this kind of fibrous structure. And typically the protein content more than 40% basically leads you to texturization. It's hard to avoid it. And this is basically showing you some crumbles from pea protein, where you get this product, you dry out of the extruder. What people do is they take this and they hydrate it, and then they will take this one, which has the small fibers, and make that, convert that into, mix it like I think in northern India, they make the soy vadi, which is basically texturized soy protein. Right. So this is a system that is set up to make high moisture meat analog. And we have a research program in this area, started working on this area for about last few years. And you can see the cooling die. I wanted to show this to you so that you can, from an engineering perspective, how do we utilize the process flow of a material. So when the product coming out of the die goes into this long cooling die, the length of this die, probably the picture doesn't do the justice, but we're putting in this picture here, the material is going in and the die is this long. The length of the die is almost the same as the length of the extruder. So it's that long. So it's and we pump in a lot of cold water so that we try to cool it down as much as possible. And you can see the material is getting compacted with the moisture content more than 50%. So if you remember flow of fluids, probably who taught us, and my classmates can tell that Polis Gaur taught it, and even Nemi Chandrapur taught it, where Nayan Gaur taught it, where they were talking about fluid flow. Inside, what happens when you put a material that is flowing into a constricted area, there's a lot of resistance on the wall side, towards the wall. But in the center of that pipe, the flow is faster, right? So that difference in the flow, or the different grades of resistance, will help you create the texture, the meat-like texture. And I think you can see that here on the product. You can see almost like a U shape. That's because in the center the product is flowing faster versus the sides. And what does that do? It creates a texture like this. So that's what they use to create a meaty-like texture. But this product, you cannot dry it. You have to basically freeze this product. So they will take this, chop into small pieces, and they will put a lot of marinade or flavors into it, and then freeze it. And people will buy this and open up the bag and fry it, stir fry it, and eat it. Not the deep frying, stir frying. So in summary, that's what happens to starch. That's what happens to the fiber. And the proteins, they will change from their complex structure to this fibrous structure. Those are the changes that happen to the major components. So if you understand how each one of these work, then you will be able to utilize the engineering and the chemistry together to create the products that are of the different textures and different tastes. That's the beauty of combining both the engineering and the chemistry. So this one, I just left it here so that when you mix, different ingredients together and try to extrude them, you really need to understand what happens to each one of them when you subject them to the conditions that you see inside the extruder. So if you understand that, then you will know how to combine different ingredients that function differently. So for example, ingredient 1 here, I try to show the color grading. This melts about this point where I'm pointing it. So the ingredient 2 does not melt under these conditions, but the ingredient 3 melts early on. So what can you do? You can actually pre-cook the ingredient 2 and then put it in, then it might perform better. And for ingredient 3, you could put that later in the extruder so that it doesn't overcook. So those are some strategies you can use to be able to modify the machine and utilize the functionality of the raw materials. Right. So some final thoughts that I have with this, it's important to always understand the material composition and the functionality of the material. So what I mean by that is, how does the material change when you put the heat, the shear, under different conditions, right? Under different pressures. So if you understand that, then you know how it will change and how I can manipulate the process to achieve the desired product that I want. And it is always important to understand how the different components interact between each other. So it's not just the single component, it's when you mix them together, what happens. So with that, you will be able to get to a product, but also with the process, if you guys remember back when we were doing our undergrad, there were unit operations we studied about drying, whether it's coating, all those things, different types of drying, like impingement drying versus convection drying, or a combination of that and vacuum drying. You can utilize those to manipulate the textures even after the extrusion process. And then finally, you will arrive at the product that you want. So, if you think about, even locally there in India, there is so many different agricultural products, so many different raw materials, and they have different functionality. So if you can take advantage of that, and you could create some really cool products up there. So the opportunities to me are endless. So that's what I wanted to leave you all with. And then I wanted to show you a few things, what we have here at WSU. The extrusion laboratory is fully equipped. We have single screws, twin screws. So that's showing a single screw there. And this one is a counter-rotating twin screw. And this is the co-rotating twin screw with the cutter system at the end and the conveying belt. And you'll see a dryer at the back there. It's a batch dryer. And that's the picture of the cutter showing from the face. And then I just wanted to share the team. This picture was taken back in 2014. So the team has been, I always had a team, really good students and postdocs. The way it works here, we know as a faculty, we have to support everybody's salaries here. The faculty has to bring the grants and support them. Some of these students have graduated and they're all working in different companies. I'll show you some other pictures here. So you'll see the ones graduated, they went and worked at different places. And this was, we currently have the lab running. Yesterday, no, not yesterday, when was it? Friday, we were running some product made from kelp chips. Kelp chips we're making. And we had a company in, these are my students, current students, a few of them. They were running the extruder the other day. And you can see due to the pandemic, we're taking a lot of precautions. They all are wearing the mask and the shield. It's very hard to work with all that, but really good students working hard in the laboratories. So with that, I'll go ahead and close it, and I will open up for questions and discussions. I really wanted to spend time talking to you all, so hopefully that we still have time for that.
Yeah, thank you very much for the wonderful session and the wonderful presentation, mainly in the three areas like protein, fiber, carbohydrate, so starch, basically starch. So how we can extrude it, and what is the most important fractions will take place. With your permission, Giri, I just share your own extrusion product which you have shared us. So this is from your laboratory only, which was shared during our session. Am I right, Giri? Hello? Hello?
Yes, that is correct.
Yeah. So thank you once again. No. So it is now, we have a different faculty members for the discussing of various clarifications, and a couple of questions has been already raised, and we have opened the chat box. It is again live on the YouTube, so you can chat in the YouTube also, and you can chat in the chat box also. We can ask the questions directly. So now may I request our Dean sir, please unmute yourself and yeah.
Yeah, Girish. Girish, audible? Is it audible?
Yes, sir, audible.
Yeah.
Girish, really, it was a very good presentation. Mainly because just instead of giving an overview of many things, you have dealt in depth with a particular technology, that is extrusion technology. So it is really very helpful, particularly I can say for students and other maybe PG or PhD students also, because giving an in-depth knowledge of a particular technology is also most important as just going through different things which are available. So really, it was very nice to hear from you. Thank you.
Thank you. Glad that was clear.
Yeah. So Nironi sir wants to say a few things.
Yes, I don't know. Am I audible?
Audible, sir. Audible, sir.
Yes, audible. Okay, fine. Girish, wonderful presentation. Congratulations. Hello.
Yeah, thank you.
Yeah.
Nidoni, your sound is very less. Volume is very less.
Sir, that is, I cannot do anything now.
Okay.
Whatever it is there, it is, no, okay, whatever. Girish, very nice presentation, and many of the things are, clarified because you dealt in detail about, because, inside what happens that people were not knowing exactly how exactly the fiber in that inclusion of or incorporation of fiber into the these extruded products, and the scope what I would like to mention here. I think there is a huge scope in India in development of these kind of extruded products. Especially we also worked with you, and we are working on development of some of the fortified extruded products, and we are utilizing the waste or the byproducts of this rice and dal industry, and producing this rice like the rice analogs and dal analogs. Now it is going on, and like that we worked on millets also. We come out with some fortified millet extruded products. That is what I think that is a wonderful thing going on in our university. And one technology has been submitted for patenting, this rice analogs, fortified rice analogs. We used broken rice from the rice industry and mixed this broken dal from dal industry, so that we enriched the rice into higher content of protein, and we also mixed nutrient mixes along with that, so that it can meet out the iron, calcium, and folic acid and vitamin B12 in daily diet of the people. In that way we developed, and the research is going on, and many of the things we also came to know about what exactly happening inside the barrel, how much the pressure, temperature, how the behavior of the flour is getting changed into the barrel. Those things are very much cleared with your presentation. Very good information, very technically sound, because understanding the product behavior, that is what you dealt very nicely. Thank you very much. And Hope we shall continue working together, okay, in the future.
Thank you, sir. Desai sir wants to ask some questions. Desai sir, please. Desai sir, unmute yourself.
Hello, Girish.
Yes, sir.
I have two questions. See, during extrusion process, the structure will change, you said. The starch structure will change. Is it because of force or temperature?
It's the shear, the force.
Because there we are compacting the product. Correct? You are using the screw. There we are compacting the product. So compaction force will be there. So also this temperature will rise.
Because of the shear, because of the force, the temperature rises. You are correct. So when it comes to expanded products, only 90% of the heat comes from the shear.
Yeah.
And only 10%.
We are providing heaters also there, no?
That is only to maintain the temperature so you don't lose it.
Constant temperature.
Yes.
Yeah, one more question I have. You said this extrusion process, is it used for preparation of chemicals?
Yes, it is. Chemical modifications.
Chemical modifications. Okay, okay.
Yes.
Because I have not heard about that.
So even like, for example, to make levulinic acid, you can take, I was involved in a project, this was, the chemical industry does it for a lot more, but you can take any chemical reaction you want to do at a high temperature. You could do that inside the machine in a continuous process.
Mm-hmm.
For example, in the food industry, if you look at some patents is where you get a lot of information, but there is the oat milk, enzymatic reaction combined with mechanical degradation. They use extruder to put in the enzymes in the preconditioner and then convert it, do the hydrolysis in the machine. Yeah.
Giri, there is one question from the audience. What about the texture of meat analog modifications?
What was the question? I think I read that. Was it a twin screw?
Yeah. Twin screw for creation of such product.
Yeah, so twin screw is really the one you need to modify texture more uniformly, but you can also use a single screw. But there's a lot in it, though. You can create really very wide textures depending on the type of the protein and the amount of the energy you can put into it. But twin screws are the most common ones used.
Okay. Wata, do you have any question? Yeah, unmute yourself.
Really very enlightening presentation, Dr. Girish. Really, I congratulate, and you really made us, focused really very well inside the part of extrusion. Actually, we are really working with this basic models of extruders which are available in this country, and one thing, actually, I have one question: whether can we make arrangements so that the temperature can be controlled immediately after the expansion, so that we can provide like a cryogenic type of a thing? Can we able to do that? Whether it can be possible immediately after the expansion? Can we control the temperature so that we can retain some of the nutrients in that?
Yeah, you can control as soon as it comes out. People have done it. People do it. One of the common things they do is, by using forced air, whether it's hot or cold, onto it, or some people will take that and extrude into a vacuum system.
Okay.
That is commonly used. Well, not very commonly used, but it is used, where it comes out of the extruder, goes into a vacuum, so you retain the expansion, and you immediately remove the moisture, so you retain the structure better. That's commonly done. And another example I'll tell you.
Are there any encouraging results about retention of nutrients by doing that?
Oh. Are you saying you want to retain nutrient because they're flashing off?
Yes.
Okay. Yeah, you cannot retain the nutrients that are flashing off. If it's a volatile, it's going to flash off because you are using flashing off for expanding. Right?
Yes.
But if if you want to avoid the expansion, then you can retain the volatiles. But if you're trying to puff it, you're going to lose the volatiles no matter what. But in products like noodles, pasta, you can retain the nutrients.
Yeah, that is cold extrusion.
Yeah, then you don't puff it, right? Yeah,
Thank
otherwise you will lose them.
Yeah, fine, Matan. So I think our Director of Education, sir, is online, Dr. M.G. Patil, sir, and also the Director of Research, Dr. B.K. Desai, sir, and Director of Extension, B.M. Chitapur, sir. Sir, any clarification, sir? You can unmute yourself, sir. Okay, if anybody is having any clarifications, you can have another few minutes.
Nidoni sir wants to. Sir, Nidoni sir wants to add something.
Okay, he can unmute himself. Sir, unmute yourself.
Girish.
Sure.
Girish, see, we have both single screw and also twin screw extruders in our lab. But what we are facing problem is, can we do this cold extrusion using twin screw? Can we control temperature and not to raise the temperature? Just it should extrude, but using twin screw.
Yes, but you have to use pre-gelatinized raw materials.
Okay.
You pre-cook the material, so it's instant starches, for example. So if you use instant starches, then they won't, raise the viscosity inside the machine. Then you'll be able to maintain the temperature to be lower than 100 degrees.
Okay, we'll try. Thank you.
Yeah.
Giri, is extrusion process is used in medical field? That's the question asked by the participant.
Yeah, I just typed it. Yes, it is used a lot. Obviously, for like I mentioned before, for making tubes and even syringes and things like that. They do use them, or injections to those plastic pieces. They're all manufactured by extrusion. But in terms of body parts, so like scaffolds, how people use pieces inside like joint replacement or any other pieces like that, those can be made with extrusion. But many times they're not the typical extrusion that I showed you for making a puff. Those would be extrusion where it's a combination of extrusion and molding. So you make the pieces, what I call pellets, and then you take that pellet and do injection molding. And that's how you make a lot of the parts that are used in the human body.
Yeah. So any clarifications from the Girish Kanjal about the extrusion process? Pallet?
Yeah. So there's a question there.
Yeah.
In the chat box about
protein bar market trends.
Yeah, the protein in general, the protein market is on the rise. Everywhere I see that protein, because as a society, not only here but throughout the world, we ate a lot of carbohydrates for the last 40 years, and then the obesity has increased and diabetes has increased. So now we're trying to see how we can add protein to the diet. So because of those reasons, there's a huge demand for protein, and bars is one of the vehicles by which you can consume high amounts of protein. And that market is going to keep going up. But what is needed in that market is, how can you keep the bar? So in a bar, when you eat it, there's like about 20 different ingredients. So each ingredient absorbs the water differently. right? So when you make the bar fresh, when you bite it, it's nice texture. But if you keep it in the market, in the shelf for 3 months, then the moisture goes here and there. Then you try to open it, it's dry. So that's the biggest issue. So if you can, develop some ingredients that are, or a technology, whether it's barrier technology or slow release technology, then if you can maintain the texture of the bar, then there's a high demand for that kind of technology in that area.
Yeah. So there is another question in the chat box. During the extrusion process, resistant starch increases or decreases?
So that depends on what you're using. If you use fat, like lipids, 3%, 4%, you cannot use more than that, otherwise it won't extrude well. But if you use some lipids, small amounts of it, that combines with the starch and creates a resistant starch, but very small amounts of it, but not a significant change. So, you may have read about it where if you take pea flour, so chickpea flour, right, that we use in India to make bhaji, right?
Yes.
So that flour, you can take and extrude, and they say, oh, the fiber increased. That means resistant starch increased. That it's possible because it's a combination, the fat combining and coating it up so the enzyme cannot go inside, so it becomes resistant starch. So it kind of depends what do you call a resistant starch. So RS2, RS3 can be created with extrusion, but not RS4. So resistant starch 4, the chemical reaction, that you cannot. So I got a question. So from somebody, it says, sir, what is used to avoid friction in extrusion process? If oil is used, does it affect the product? I think I answered that partly. To avoid friction, then you better don't want to do extrusion, right? I mean, the purpose you want to use extrusion is to, you take advantage of friction. But let's say you want to just use it as a mixer, right? Yeah, people do use extruder as a good mixer. Then you don't want friction. Then yes, if you coat with fat, when I say fat, any kind of lipid, it will release, it won't stick to the walls. But the problem is, it will also go and coat the food particles. Then the particle to particle, it's not going to blend in. So then you have other problems that come up with that.
So there is another question, Giri. So is there any specific purpose of fractionation of these materials?
Yeah, so fractionation we do in the industry because, so if you, let's just take chickpea. When you take chickpea or besan flour, it has what, 20-25% protein in it. Now, if I want to make a product that is high in protein, low in carb, I cannot use besan as it is, right? So then I can fractionate it so that I separate the protein and the starch. Now I can go maximum maybe 90% protein, right? So that's really the purpose of fractionating. So you get the pure forms of the individual components. Then you can design the product the way you want it, not only for nutrition, but also for texture.
Okay. So there is a question from Anil. Any studies has been conducted on fruits and vegetables for extrusion products, specifically tender jackfruit?
Well, in general, fruits and vegetables, absolutely. When you think of an ingredient, I mean, any food material that we eat. So let's just say mango fruit, for the purpose of example. So you take a mango fruit, 80% of it is water that comes from the tree, right? But when you cannot put that in the extruder because that's a lot of moisture. So what you would do is you will juice it, so you remove the moisture or dry it, and then you make the powder, then you run through the extruder, right? That's where you can get a shelf-stable food. But when you take one mango and remove 80% of the water, now you got down to only 20 grams of the mango powder, right? Now you put that into the snack product. You cannot create, because now it has a lot of sugar. Okay? Fruit has a huge amount of sugar in it, right? But if you take the whole pulp, you do get the fiber too, which is good. But the quantity of the sugar is so much that you cannot extrude by itself. You can maybe create a leather type product, where like chewy leather type product, but not a puff type product. So people do extrude. You know, what they do is they will take different kinds of fruits, blend them all together, remove the moisture, dry it as much as possible. So you use a evaporation process that we learned in the unit ops, and then you will get this thick sugary leather, and that you can extrude to create like a strip or like a belt, you know, like a leather belt, and that becomes a very dense, nutritious product. So that's a different type of extrusion. And I don't know about tender jackfruit. I had to look it up. I'm not sure.
Anil, I hope, is it clear? If it is not any clarification, you can unmute yourself and you can directly ask the question to the.
Yeah, hi Girish. Actually, I just wanted to ask you, tender jackfruit being now replaced with, for the meat. So in the many countries, so we were doing a lot of R&D on the preservation, basically like a pickle product. So by seeing your the process, I was just thinking like, can we do, because the product is similar to the meat product. Maybe the nutritional and other parameters are much richer in tender jackfruit. So maybe that can be one of the for fruit, or we can say can be used in this extrusion process.
Yeah, I know.
Small interruption. Giri, I think you have not stopped your screen sharing. Can you close it?
I don't think, is that my screen?
Yeah, it's, I think your screen only. Can you check that?
Hold on. I don't think so. I'm not sharing the screen.
It's not sharing.
On your end? Oh, let me share my screen.
No.
Okay, there you go.
Yeah.
Anil, that's a good question. So I did hear, so in case of jackfruit, I did read about that one. What they're doing is the jackfruit also contains some hydrocolloids in it.
Mm-hmm.
It's the hydrocolloids that are benefiting its usage in meat analog products.
Yeah.
Okay. So that's really, I think, where they're getting that texture that is needed. I'll give another example. You may want to look this up. You know those hesurka, mung bean? We still have them, right? In the, we eat them. I ate it yesterday. So there's hesurka,
green gram.
Green gram.
So those actually have the protein from that has really unique texture.
Okay.
And the company, it is so funny. It tells you, the Western culture are so business minded. They really know how to market things, right? So there's a company here called JU.est. Okay, you should look it up. What they did was they took the mung bean and then or hesurka and converted the protein from it, and now they use it as a plant-based egg product.
Oh.
It acts like egg protein. And we've been eating that for centuries, right?
Yeah, true.
So that's, we really had to look at those functionalities within these different materials we use.
Mm-hmm.
And there's a lot in the Indian culture where, if you just go like Ayurveda, if you go back to the Ayurvedic medicines and stuff, and not even how to go there, but even like Indian cooking, traditional cooking, right? There's a purpose we use different ingredients for.
Right.
Those are the ones, if we understand why and extract that particular compound, you can create $1 billion business out of it.
Yeah.
Yeah, here is another question from the YouTube. Tomato waste pulp, can we prepare extruder for vitamin A rich processed food?
Yeah, tomato waste, absolutely. We should stop calling that as waste. Tomato byproduct, processing byproduct, basically it's that's the healthier part. When you take juice out, you take the water and the sugar out, then the leftover material is very nutritious. You can take that, absolutely, and you can pretty much protect everything that is in it, but when you dry it, you want to dry it at a lower temperature. If you dry it at a higher temperature, you do lose a lot of that nutrients that are volatile. So if you dry lower temperature, you can powder it, then put it back into the extruder and make different products with it.
So there is another question. I think you might be seeing the chart box. Any study regarding to optimize the extruder speed and voltage of machine according to the product?
Oh yeah, there's a huge amount of work that still goes on for that. Yes, you can. And the only place I have seen that is if you look at companies who are making the same product again and again for years, right? So an example I'll give is a Kellogg company who makes breakfast cereal. That's where I have seen it, where they have so much data on the energy consumption for their machines for using the same raw material again and again, right? They have developed, some of those companies have developed really good models which can control and optimize the energy consumption with it. But you can do it too for any machine. One thing you have to give attention to is your raw material fluctuations. So, in the world of food, we deal with the agriculture product, which is never the same. Okay, the quality of the raw material is going up and down, right? So when I used to do modeling initially only. I never thought about raw materials. And my mind was going as engineering only. So then I saw that, gosh, I'm assuming that everything is constant coming in. And then I'm trying to model the system, which is not true. So, but if you are able to consider the raw material fluctuation in your model, then you can optimize it. Yes.
So any clarifications from any participants, please either chat or you can text it in the YouTube also. Maybe another few minutes, we're going to close the session. Any clarification? Dr. Pallel, you can unmute yourself.
Yeah, Dr. Girish, Panja,
sure.
Thank you for your wonderful presentation on specifically extrusion products. I think it is a basic source of protein in the US. I think you are working more on that one. I was also having the same doubt whether fruits and vegetables can be made into extruded products. I think you have clarified to Anil Nayak. Okay. Thank you, sir. Thank you for your wonderful presentation.
Yeah, thank you. Dr. Muski, sir, you can unmute.
Hi, Girish. Hello.
Yeah, it's audible, sir. Go ahead.
Okay, wonderful. Thank you very much for your wonderful presentation, Girish. You have really made a good effort in making the presentation very interesting, covering the overall the view of explaining the extrusion of the food materials in a simple and a nutshell. So I'm just wondering, in India, extruded products like pasta, breakfast cereals, and kurkures are increasing day by day. But apart from having the advantages of the extruded products, there is a lot of debate on the reduction of essential amino acids, then destruction of vitamin A, then maybe the potential increasing risk of obesity. Is there any way to decrease all these the ill effects of the extrusion?
Okay, so in general, actually extrusion does not eliminate amino acids. So you will retain all the amino acids that you put in. And even the vitamins, I know there is some studies out there which say that you lose certain vitamins. The vitamins you lose are the vitamins you will lose even in regular cooking. But why does the obesity numbers you see increasing is not because of extrusion reduced or any other process, though it doesn't matter extrusion, whether some other process too. It's more about the raw material that is used to make those snacks. So let's take an example. You think about kurkure, right? The base of kurkure, which is excluding the seasoning they put on it, just the base that comes out of the extruder, that's about 20 grams out of 28 grams of the serving. And out of that base, 90% is starch, right? So it's the carbohydrate, the empty calories we are consuming. And then the rest of the material, which is the seasoning and the oil that goes on it, typically that particular product contains about 36% fat. So in other words, if you eat 100 grams of kurkure, you are eating 36 grams of oil in it. I mean, literally that's what you're doing. So it's not about the extruder piece, it's what they put in it in terms of the raw material. That's what we need to control. You'll go to the market, you will never see or rarely see a whole grain product. And that's simply because it's hard to extrude it. I mean, you can extrude, but it won't taste good. People won't buy it. So people will buy what tastes good, right? I think the challenge is for us as a scientist or the industry is to really see how can we make the nutritious product taste good. That's really where I think there's a gap, and the science is advancing. Now people are developing this receptor, they understand the receptor cells in the tongue, and now they're trying to create compounds that, even though you eat it, even though it's healthy, but it tastes like regular fat. So then people love it, right? So you're faking the system, the receptors in the mouth. So that's sensorial effects are tremendous in food industry. We want in at home, if let's say you cook some vegetable, but if you remove the salt from it, or let's say we don't fry, like Karela, okay? Karela is important. We need to eat it, right? But does anybody eat without frying it? Very rare, right? So that's really the reason. It's not necessarily that the extrusion breaks it down. Actually, extrusion retains all the nutrients except the fuels, which are due to the temperature effects.
So there is a question, Girish. These extruded products are having the plastic state. Is it really a plastic?
So can you ask that question again?
Yeah, so it's in the chat box they have sent. So these extruded products are in a plastic state. Is it the plastic?
So you really need to understand, plastic state does not mean it's the plastic that you see. It's the plastic tube or something. It is the state of the polymer where it goes into. So that's really, it's the characteristic, whether it's bendable, whether it's movable, how much resistance does it have towards the flow? That's what they're measuring. It's not the literal plastic.
No, see, the question may be in a few months back in most of the TV channels that they have shown.
Okay.
Yeah, so these extruded products are made up of plastic, so it is not supposed to consume like that. And even in rice also they have claimed it's a plastic rice. So
that's
really true. Is it really true? So that may be the question.
Okay, so that is really not what I call that issue is an adulteration issue or a food safety issue, right? So that's like people putting, if you remember a few years ago, melamine into milk powder, right? It can spike the protein level at a low cost. So instead of adding rice, maybe they put in this, I don't know, a cheap plastic that was, shaped like a rice. But I don't know, it will take a lot more money to make that versus just giving rice. It depends on, my guess is it's just somebody trying to mess up the system.
Yeah. I think if any clarifications, maybe another 1 minute, we can have a chat box. Or so, dear participants, we'll share the your feedback form maybe another few minutes. Please fill the feedback form and ask the questions through the feedback form also. So for any clarifications. I think we have received just one more question. Any entrepreneurial opportunities in jackfruit processing in Malnad region of Karnataka, other than the chips and ram fruits?
Yeah, so the jackfruit, as we were discussing with Anil Kumar about, its ability to have that stickiness, and so the best thing to do is to fractionate that material and extract the hydrocolloid out of it. Then I think the value of that will be much more higher than just the jackfruit chips. So you may have to look at the fractionation of that material.
Okay. I think Desai sir came and our director of research. So okay, we have any questions, sir? Director of research, Desai sir. Okay, so they might be busy. So anyway, thank you very much, sir, Girish Ganjal, for your wonderful presentation. Now over to Dr. Ramappa Keti for the summarize the presentation and say a word of thanks. Dr. Ramappa, please.
Yeah, it is almost 1.5 hour. Very good presentation on the application of extrusion. Am I audible?
Yes.
Yeah, okay. So thank you very much, Girish Ganjal, for your overall very good presentation on the extrusion process. Actually, we have covered so almost all technical aspects with respect to expansion, texturization, and main importantly, transformation of many of the food ingredients like starch, protein, and lipids. So what actually it is going in the extrusion process. And again, your pictorial presentation was highly appreciated. And one more very important aspects you emphasized was the need of food chemistry with engineer. So mainly to understand as well as in the food product development. And again, we have emphasized on actually the area in the development of analogs through extrusion process. So there is a huge scope is there for the development of analogs. So it may be meat analogs or any other texture based they look like type of material, and again there is a way forward from extrusion process. And again you have throw a light on multiple ingredients management in extrusion process. That is also one more very important area wherein so it is not that all ingredients so having the same effect in extrusion. So different so ingredients has to be take differently in extrusion process. That is what again one more very important area you have touched upon. And at the end the interaction section was also very meaningful, and many participants so they have clarified many doubts with respect to extrusion technology and overall for a food processor, as a food processor. And again, as I am also in the food processing area, and I really thrilled with your presentation, audio visual presentations, so that so many technical aspects you covered, and it was a very meaningful and very highly informative presentation. And on behalf of University of Agricultural Sciences Raichur, and on behalf of College of Agricultural Engineering Raichur, and on behalf of from all the participants, my heartfelt thanks to Dr. Girish M. Ganjal for your time, as well as for your very nice presentation with respect to extrusion and technology. Thank you, one and all.
Thank you, Thank you, Dr. Ramappa, for vote of thanks. Once again, on behalf of, I think, any clarifications, because we have another 2 minutes. Just now, I think our Dean of Agri Engineering, Dr. Suresh Patil, sir. Sir, do you have any? Sir, what is your ID, sir? I'm able to.
Dean.
Yeah, sir. Sir, you can unmute yourself, sir. So please unmute, sir.
ಶರಣ ಏನಿಲ್ಲ ಕೇಳ್ತೀನಿ.
Yes, sir. Yes. Okay. Okay, right, sir. Thank you very much, Dr. Girish. So this is a small announcement to the.
1 minute, Dr. Sharan.
Sir, Dr. Girish.
I am really happy to listen to Dr. Girish Ganjal. Particularly his explanation for the questions really mesmerized me. one point you asked about many products that have value in India. You spoke about this jackfruit also. Like that, there is also demand for this coconut sugar, jaggery. I think you know it. So some palm extractions are used to produce jaggery. So these have also got good market, and if they are taken to abroad or other countries, I think our farmers can really be benefited. So you can make our engineers also how best we can go ahead in this direction or in using these traditional materials. Thank you.
Dr. Girish, can you
Yeah,
respond?
thank you. Thanks for that, for the comments and for the suggestions too. So I think definitely there is opportunities out there, and I think even like locally in India, there's so much diversity in terms of crops that's grown, right? I mean, considering not only the grains and the fruits, vegetables, but a lot of other things. So you are absolutely right with the coconut, but also with many other things like that mung bean example I provided. Definitely opportunities, and we really have to investigate. Maybe pick up a few and investigate and commercialize them. And in terms of commercialization, now actually it becomes more easier as the world has become smaller, so small that you know you can immediately find investments or private partnerships from anywhere, right? So you can bring in the investments pretty quickly. And now that over the last 20 to 40 years, we have had people from agriculture universities. Just an example, right from Raichur and even from US, the Harvard, where it was US Harvard before. The connection is huge. So we could actually, we should do something where maybe it's an alumni network or some sort of a network we create. And out of that, maybe even if we get one or two ideas to fruition in the next 10 years, that would be fantastic.
Definitely, Girish. You
Right,
can,
sir. Right, sir. Well, explanation is really very good.
Thank you.
Yes, sir. So definitely we can collaborate because we have already MOU between the Washington State University and the University of Agricultural Sciences, Raichur, sir. So we'll extend our further network. In last 4 years back, we did one collaborative project between the WSU and USR, sir. So thank you, Dr. Girish. This is a small, before closing the session, I want to have a small announcements to the participants. We have an afternoon session at 3 o'clock. There are 3 participants, Musawir A. Patel, Girish Deshpande, and Anil Nayak. And followed by, we have a valedictory session chaired by our Director of Education, Dr. M.G. Patil, sir, and guest of honor, our Dr. B.M. Chittapur, sir, Director of Extension. And this is our, in the afternoon session, on behalf of the University of Agricultural Sciences, Raichur, College of Agriculture Engineering, Raichur, and whole fraternity from the Karnataka, I can say the whole fraternity from the Karnataka scientists. So I extend my sincere thanks to Dr. Girish, because now almost it is 10:30 for you, late night for you. So thank you very much for your wonderful presentation, wonderful time. So definitely we'll connect in coming days. Thank you very much for your time. Thank you, Girish.
Thank you. It was my pleasure. Thanks for having me. It's really nice to see at least some familiar faces and also meet some of the new faces here as well. So greatly appreciate it.
Yeah, thank you very much. Stay safe and be safe.
All right.
Stay home. Yeah.
Stay safe.
Yeah. Yeah. Jai Hind.
Bye.
Jai Hind. Bye. Bye. Bye.